You might have a reinforcement learning supervisor that's deciding when to use the rule set, when to use, control theory, and when to use, a learned policy. And in that way, you're building from building blocks a customized intelligent system for that specific task. Your competence and your expertise or your autonomy level is actually based on your practice, not based on your intelligence. So if that's true, then each task could and should have a specifically designed set of skills and agents. Each of these patterns is additive. So you can build a bigger agent design that has a strategy pattern, a perception pattern, and a plain execute pattern together based on the needs of accomplishing that task. But what machine teaching tells you is that intelligence combines those different modular pieces. So a multi-agent system can absolutely have predictions in it. And the agents can access those predictions to get more information than what the sensors provide. And there can absolutely be rules-based systems as fallbacks when we don't really know what to do or when it's very safety critical as part of the team of agents. In the same ways, I think of it very much like...
Welcome to the AI in Manufacturing podcast here on Industry 4.0 TV. I'm your host, Kudzai Manditereza, and in this episode, we discuss designing autonomous AI agents for industrial operations. And my guest on this episode to help us unpack this is Kence Anderson, who is the CEO and founder of AMESA. I hope I pronounced that right, Kence.
Both right on. Kence and AMESA, you got it.
Great stuff. Welcome to the show. It's really great to have you on here today.
Yeah, it's nice to be here.
Cool. Yeah. So before we, dive into the topic of the day here, could you maybe take a moment to introduce yourself to our audience? Tell us a bit more about your background and a bit about AMESA.
Of course. Thank you. So my background academically is in mechanical engineering, but I spent my whole career in software and out here in Silicon Valley, mostly in startups, almost exclusively in startups. So I started off at IBM, and from then on, I've been working at a series of technology startups. And for the last 8 years, I've been focused exclusively on how to apply autonomous systems to manufacturing and logistics, or what I call industrial autonomy. So especially in 2017, 18, 19, where I worked at a startup called Bonsai, and then Microsoft after an acquisition. I traveled all around the world, going to all sorts of industrial sites, steel mills and chemical plants, mines, oil refineries, talking to, yes, the leadership, but spending a lot of time walking the plant floors and talking to operators about how they learn and how they teach these high value tasks in manufacturing and also in logistics. And over that time, I developed a kind of a methodology that I write about in my book, and that's the foundation of AMESA. And I call this methodology machine teaching, and it's really about how skills are learned and practiced.
Awesome. Yeah, really looking forward to diving deep into that a little bit later. But before we get into the AMESA platform itself, I want to spend some time on kind of like the bigger picture here on why industrial AI needs sort of like this new paradigm in the first place. So, I mean, when you look at how manufacturers are deploying AI today, where
Yes.
do you see the biggest gap between the promise of AI and what's actually happening on the ground?
Fantastic question. So most of what people call industrial AI, I mean, I venture to say more than 95% of what most people call industrial AI is either storing and manipulating industrial data or OT data. That's important. Connecting software to the plane. So, IoT is what people usually call it. So mostly it's about the data and it's about the connection to the plane. kind of like the Scarecrow and the Wizard of Oz. If I only had a brain, what's missing is the actual intelligence that can perceive and act. So yes, there is quite a bit of activity in computer vision. Yes, but that's missing the action. And I've always said, perception is always in service of action. Especially in industrial, there is no perception that isn't designed, that isn't for the express purpose of taking an action. And so that's the biggest gap. That's the biggest gap is how do we augment, uh, codify, store this mostly human intelligence about how to make these decisions in industrial plants.
Yeah, that's really super interesting. And also, for me, the reason why I find sort of like agentic AI so powerful, because there's this report that I read from the American Labor of Bureau statistic, which talked about this idea that for the past, I think since 2008, since up to 2013 or so, most of productivity in manufacturing has been stagnant, has flatlined, and that's the period where we were actually doing this connection that you're talking about. We are connecting, getting the data out. So what that means is that the bottleneck was never the data access; it was that missing, intelligence, like making sense of the data, right? 100%. So then, how do you? I mean, you have written that technology R&D has forgotten development, and that we have gone from research to deployment pipeline to what you call research to PR pipeline. Can you unpack that for us, and maybe specifically, if I'm a manufacturer trying to figure out what is industrial AI, what's production ready versus what is still a science project, what should I be looking for?
Yeah, that's a great question. So first, let me tell you what I mean by this kind of press to or research to PR pipeline. So I think this first started happening in mass scale with DeepMind's fantastic, research breakthroughs, which we started to see as early as 2013 with, uh, the invention of reinforcement learning, and then, reinforcement learning's ability to uh, master the game of chess and Go by practicing against itself and beat the best Go player in the world. Uh, play games like StarCraft, even fold proteins and things like that. But those papers and the research was published, and then it's quickly kind of it's not adopted. It's the hope is that that means that we could do something with this at this moment. And I first experienced that with deep reinforcement learning, and I think it's happening now with generative AI and agents too. And research and development is a process where these breakthroughs get passed over to engineers, frankly, that figure out how to make this work in real life. And so most of my time in this field has been spent figuring out how to make reinforcement learning work in real life. Now, the first thing I would say is my first kind of hypothesis was, okay, reinforcement learning imitates or approximates how humans learn by practicing. So when I went into different plants, some of my AI research colleagues, this is way back in 2017, 18, 19, were telling me, oh, you should use this algorithm to improve operations. You should use that algorithm. And what I found quickly was when I interviewed folks, there's no algorithm. That's no state, no stock algorithm that can approximate human learning when it comes to practicing, these tasks. And I can give you an example of the kind of tasks later if you'd like. What I found that people were doing was, one, they were practicing for 5, 10, 15, 20, 30 years to get good at this. And the second is they were being taught. So that's where my methodology kind of really took off, is this idea is, well, if AI can learn, you should probably teach it something. I mean, I often ask in my courses and workshops, Who in here has never been taught anything? And no one can, not even the smartest person can raise their hand and say no one's been taught anything. Teaching is a way to bound practice to promising areas where you're likely to see success. So it's this, that's the development phase of it, was going, and I will give you an example now. This is some work I did with a major beverage manufacturer while I was in at Microsoft, and it was publicized, and we were taking an extruder that made snack foods, Cheetos snack foods, and it takes a human being at least 10 years to learn how to control this thing well. And we applied reinforcement learning, and I tried to tell the researchers, if you just let it practice by itself, this is not going to go well. And it went okay. Like it practiced for a long time, and this is all the way into like actual connection to the machine and real trials in the plant, and it performed okay. But it wasn't considered an expert operator. It was only considered an expert operator when I interviewed the expert, and he broke down the different skills that are required. And he said, if the Cheetos are turning out right, you should use these skills in a sequence, and if they don't, you should use this skill. And when I built a team of agents that learned the specific skills that these operators are taught, expert operator. And so that's an example of this development process where the research itself is missing the practicality of how to make it work in real life.
Oh yeah, absolutely. And from what I get is that this it's this whole idea that for AI to work in at scale, you shouldn't use sort of like the enterprise first as proving ground for AI, specifically for manufacturing environment. And in case this really needs saying, can you please sort of like paint a picture for audience on what's actually at stake here? What does it look like when manufacturers get this wrong and they deploy AI that is not
So the thing that one of the things that's most challenging for me and my customers is what we call pilot purgatory. So when you rush in to use a technology just for the technology's sake, and I've seen this so many times, someone is excited about a technology, and that's great. I'm a technologist, and I get excited about technology too. But if you don't have an understanding of the tool and why to use it, then you'll apply the tool wrong, and then you'll lose momentum for innovation in the organization. And there's only so much. A manufacturer's job is to make things, to make and move things. Manufacturer's job isn't actually to innovate. So there's only so much bandwidth for innovation. And if you spend that bandwidth, you misallocate that bandwidth on technology experiments that are missing the kind of systems understanding of the right tool for the job, then you're going to get, the organization is going to become disillusioned. You're going to waste a whole lot of time.
Yeah. And I think you mentioned also this idea that you can't just deploy AI and hope that it will figure out stuff on its own, like it will learn on its own. Want to sort of like dive a bit deeper into that? If you could explain to us on where exactly does like rule-based automation or your standard machine learning hit the ceiling? Why is it
Yes,
so difficult?
of course. So one thing I teach in my courses and I write about in the book is there's really only four ways to make decisions. One is you can calculate what to do, and that's what control theory is. A lot, I won't say most, but probably most automation in factories based on control systems. It's some equation that describes first principles physics and says, based on what we know about that, this is what you should do. The problem with that is there is no equation for the way that complex realities come together, the way that like fluid dynamics and thermodynamics and heat transfer and all these things come together, and it becomes so complex and nonlinear. The only way to control the system is to learn by practicing. Okay. The second way that you can make decisions is what optimization is built on. You search options, and that is great in some circumstances, like maybe chess or something like that. But it's very, very brittle to changes in the environment. And we all know in manufacturing, that's the thing that makes it hard, is variation of volatility. Okay, the third way that you can make decisions is to look up past experience. Now, the great thing about that's what a rules-based system is. That's what an expert system is. Now, the great thing about that is you are looking up past experience. You're looking up against things that have worked. But the way that you codify that is in these rules, these rigid rules that have a hard time with the nuance. The fourth and only other way to make decisions is to learn by practicing. And in my paradigm, you can actually mix and match these freely. So, for example, you as a human in a factory, sometimes you're actually calculating what to do. And sometimes you're searching through options. You're certainly learning by practicing. And sometimes, you're taking someone's rule, as a starting point for your practice. Like when someone in chess says, protect your queen. You don't always need to protect your queen, but you're taking that rule as a starting point for expertise, and then you practice and figure out when you should protect your queen, when you should. In the same way, a team of agents can combine those. This is the systems approach. The team of agents can combine those things. You might have a reinforcement learning supervisor that's deciding when to use the rule set, when to use, control theory, and when to use, a learned policy. And in that way, you're building from building blocks a customized intelligence system for that specific task.
Okay, so and this is where the idea of machine teaching comes into the picture, I suppose. Can you maybe unpack that further for us on exactly how machine teaching is different to these traditional ways of capturing data?
Yes. The idea, so first let me just step back and talk for a second about the idea of teaching. So the idea of teaching is this. I mean, there's elementary teaching, which is just teaching you facts, like what you have in preschool. This is red, this is blue, this is A, this is B. Okay, that's teaching. But once you get to more sophisticated levels of teaching, you're actually giving guidance about where to practice and what to practice. So when you go to basketball practice, then your coach says, I want to teach you the jump shot. Now, there's an infinite number of ways that a biped with two arms and two legs could try to launch a basketball into a hoop. An infinite number of ways. And what the coach is saying is, hold on a second. You're going to get the most success if you put the ball right here and you push the ball out of. Now, where did that come from? That came from experience, from collective experience. That doesn't mean it's not a rigid rule. There's not only one way to do that. So if you can have a jump shot that starts here, starts down low, starts up high, but he's saying, I want you to practice within this box. I don't want you just doing this, because that's not a promising way. And so he's teaching you skills. So that's what a chess master does. It teaches you different strategies and different skills to practice. And that's actually how you get farther along, as you learn different strategies, which to the basketball analogy might be the jump shot versus the layup, which the layup is for when you're closer to the basket in general, and the jump shot is when you're farther from the basket. What's the point here? The point here is you're taking collective previous experience from the problem, and you're breaking it down into specific areas to practice. Now, the amazing thing is, when I would go and interview these operators, that's exactly how they talked about operating these manufacturing lines. I was really surprised. I was almost shocked. They said, oh, there's these different schools of thought, which they're strategies. They're saying, oh, if the situation is like this, you should do this thing, kind of thing. The situation is doing this, you should do this kind of thing. Situations like this, to give another sports analogy, it's like in American football. There's running plays and passing plays. There's plays where you throw the ball, and there's plays where you run the ball. And these operators were telling me, this on this machine is how you throw the ball, and this on this machine is how you run the ball. Both are very valid things to do, but you have to do the right thing in the right situation in order to succeed. So let me give you an end-to-end example. Fortune 500 glass manufacturer. They make lots and lots of like glass bottles. And there's this machine that is very complex. It's 60 degrees of freedom, 60 set points that need to be set every minute or so. No human being had ever, no automation had ever made the decision. Only human beings. They had never figured out a way to automate this at all. We took data, and the data is used to create a simulation. If you're going to practice, you need feedback that will tell you what will happen if you do something. I'm not talking about a full digital twin or a world model. I'm talking about a machine learning model that will say, if you try these 60, if these are the 60 set points, this is what will happen. This will be the yield, for example. Okay. Then we interviewed the expert, and the expert said there's 8 different strategies. And some of them are in a sequence, some of them are in hierarchies. And we built one agent to learn each of those strategies that the operator told us about. You could also see these strategies in the data, by the way. But then that entire team of agents would practice in a simulation, just very much analogous to what this human operator did for the last 10 to 12 years. This agent learned so much in about 2 weeks of practice on the cloud, learned so much that it actually taught the human operator something he didn't know from 12 years of practice about how to do this. Because all practice is exploration of this space, right? Now, the beautiful thing is this operator wasn't threatened. This operator didn't feel, bad. This operator felt like, now I have a teammate, an AI teammate. They gave it a name, they gave it a little acronym and all this, because it learned the skills that he taught it.
Yeah, that's super interesting. It sounds to me like you're essentially taking the knowledge and kind of like thought processes of experts or operators and sort of like imbuing that into an AI agent.
Imbuing is a perfect word. It's a perfect word.
I guess my question is that knowledge also extensible? I don't know if that's the right word, but I guess the point is that even for an expert operator who has been running a line for 10, 12 years, they're also discovering new things about like scenarios that they've not encountered before. Does that mean? Yeah.
Let's talk about extensible and reproducible, right? Or reusable. So the example I love to use here is chess. So, remember Alpha Chess and AlphaGo that in 2016, they learned by practice. They didn't get taught a lot, even though in my book I do describe they did get taught some things. That the press said they just learned by themselves, but they were taught some specific things. Okay. But they learned by practicing on their own. Now, the Alpha Chess, which ended up beating lots and lots and lots of grandmaster chess players, learned and executed the 12 most common opening strategies in chess. One of these strategies is 1,000 years old. So the question is, because this was really interesting to me, when I was at Microsoft working with just some of the most brilliant AI researchers on the planet, people used to say to me sometimes, Kence, learning human strategies is like crippling the AI, because AI could be doing all kinds of brilliant things and you're crippling. But this provides evidence to the contrary, because humans, when they played chess, discovered these 12 strategies. AI, when it learned without considering what humans were doing, learned the same 12 strategies. Why? Because those strategies are required for success in chess. They're part of the landscape. Like, imagine if you opened your door one day and there's like landmines everywhere or La Brea tar pits are everywhere. That's what chess is like. That's why there's opening strategies. Opening strategies guide you through this crazy, set of tar pits or landmines where you can lose instantly in chess. And it's about the landscape of chess, not about what humans think or AI thinks. So my hypothesis is that every task, playing football, chess, operating this glass machine, has this landscape underneath. And as you explore it, you find different landmarks that need to be navigated around, and that's what strategy does. So first thing you should do is interview, whether it's agents or humans, it doesn't matter. Interview the people that have previously explored the space and find out what strategies you already know. No sense in doing what DeepMind did and spending $100 million learning a 1,000-year-old strategy. Then you can spend your precious exploration discovering new areas. To continue the chess strategy analogy, I really enjoyed this Netflix show called The Queen's Gambit. It's old now. It came out during the pandemic. And what they talked about was how in the 60s, the Russians and the US players played very, very differently. Very differently. And the Russians would watch every single, in the show, the Russians would watch every single chess match with the Americans. Why were they watching so intently? Because the Americans played in a different part of the state space that they aren't used to playing in. So it's like they were watching the proxy exploration. So yes, there are places where we've never been in these huge spaces, and there's a couple ways to do it. You can have one is if you learn the strategies that exist, and then you have supervisory agents, the ones that are selecting strategies. If you give them the authority to make a decision, if there's no appropriate strategy, then they'll learn strategies that aren't already known. So I think this aspect of exploring new spaces is very core to the machine teaching methodology.
Yeah, absolutely. And I think, when it comes to multi-agents, this idea of multi-agents, this kind of like
Yes.
where there's a friction, or it requires a mindset shift, specifically when it comes to manufacturing, because when people hear AI, they think about this, one monolith system.
This very monolithic, and can we just talk about that for a second? Because I would like to hear your thoughts about why you think that happens. But I think that one hypothesis or assertion is that I think we kind of hope for this one, you know, brilliant monolithic thing because the world is messy. Like it takes a lot of effort to learn different strategies and it takes years of mastery. I think we're hoping that someday something will be able to do all these really hard things without teaching and learning. And I don't think it's possible, but I think that's a hope we have. Maybe there's some master algorithm out there. We won't have to worry about all this minutia of what it takes to succeed in this task.
Yeah, 100%. Couldn't agree more. And I think also it's been uh, what is has been preached, in the industry for the past, 10 years. This idea that get all of the data, send it to the cloud, push it into this big data lake or warehouse, and someday the AI is going to be capable enough to make sense of everything,
You
right?
couldn't agree with you more. When I was, working at Microsoft, I saw this, and Microsoft isn't the only company that does this. I mean, all the major cloud providers, do this. And there was this one. I mean, there's money to be made in storing data, so I get that. But in some ways, it was kicking the can down the road. I mean, back before reinforcement learning, it was supervised learning. Supervised learning is what powers predictions, and it's in early computer vision, not the earliest computer vision, but early computer vision. And it was kind of like, it's almost like, well, this is the algorithm we have. So, a prediction is all you need. A prediction will solve everything. You remember that. You remember when there were entire companies, I can't remember which one it was, but there was a real estate company that decided to start, buying property, arbitraging properties exclusively based on predictions. And it went out of business in, two years because a prediction isn't all you need. But what machine teaching tells you is that intelligence combines those different modular pieces. So a multi-agent system can absolutely have predictions in it. And the agents can access those predictions to get more information than what the sensors provide. And there can absolutely be rules-based systems as fallbacks when we don't really know what to do or when it's very safety critical as part of the team of agents. In the same ways, I think of it very much like an organization of humans. Like not everyone does the same thing. Not everyone has the same skill set. And the best teams are the ones with the right set of diverse skills organized in the right ways.
Yeah, absolutely. And I think, talking about how we have already organizations, or how we're organizing talent in a manufacturing, we already have, you know, um, patterns, as it were. Some of them, adopted really from, since, the invention of management science and things like that, and some of it we just adopted without any questioning that at all. And when it comes also to multi-agent or deploying multi-agent systems in manufacturing or any environment for that matter, there's you need to design how these agents actually collaborate. It's not a matter of just putting them all out there. And you've published some really detailed work on these multi-agent design patterns, with things like your strategy pattern, some agents doing the planning and the execution, and then you've also got some perception layers, as you mentioned. Can you, maybe for the benefit of our audience, break down for us what is this idea of multi-agent design patterns, and why does getting these patterns right matter for agent design?
Well, thank you so much for actually taking some time with the material and the methodology. I appreciate that. Um, I love the concept of design patterns. They're these kind of repeatable templates for organizing intelligence, for organizing anything like software or people, but in this context, for organizing intelligence. And the first thing that this is built on, these design patterns are built on, is that each that expertise is task specific. So autonomy and expertise is task specific. So the concept of AGI is not that helpful, because even though I'm really intelligent, no one's gonna let me work in a steel mill because I don't have the expertise. Like, I haven't practiced in a steel mill. Like, you could be a great driver but a horrible chess player and be a great steel worker. Like, your your competence and your expertise or your autonomy level is actually based on your practice, not based on your intelligence. So if that's true, then each task could and should have a specifically designed set of skills and agents. Like, your multi-agent system to play chess is going to look different than your multi-agent system to play soccer, which is going to look different than your multi-agent system to play to run a steel mill. Okay, that's the first assertion. You need a customized set team of agents for each task. Okay. The second assertion is that expertise decomposes into skills. We talked about chess strategies. We've talked about football plays. We've talked about all the, and they're the exact same things that happen in industrial. So I go in and I interview the expert, and he tells, and I ask, well, what are the different scenarios? A scenario is a different situation. Back to the football analogy, when you're about to get scored on in football or soccer, you better be running a defensive play.
Yeah.
And if you're about to score, you should be running an offensive play. They're almost opposite things to be doing. And the same, so I'll interview the expert, and they'll say, "Oh, these are all the scenarios." In fact, in our platform, we have algorithms that will identify operating regions and show them to you visually. Like, oh, there's 6, 7, 8 different operating regions. Each operating region is where a different skill is required to succeed, or a different strategy is required to succeed. And it's really easy to map those directly to agents. Okay. Now, I spent a lot of time doing this and teaching folks to do this, and realized that there were recurring, repeatable patterns across these many different problems. I've done this in over probably 250 different, use cases for Fortune 500-ish companies, and certain things kept coming up. So, for example, people kept saying, well, one person will take some sort of visual input, or take some sort of sensor input and set a set point, and then an automated system will execute the set point, because they're fundamentally different things. Setting the set point and executing the set point. It's like setting the strategy and executing the strategy. And that's where I developed a design pattern. I literally saw it over and over, and I was like, oh, this is a common way that intelligence needs to be organized in industrial. Another that I saw was choosing between different strategies. That's the strategy pattern you were referring to, where let's just keep the football analogy for a second. Should I run a running play, or should I run a passing play? In general, you should run a running play if you need to move the ball a short distance, and a passing play if you need to move the ball a larger distance. But if you have the supervisor that's determining which play to run, football play caller, if that is a learning, then entity, then you can have a nuanced policy that says it's not just based on how close you are, because sometimes you'll succeed by running a passing play when you're, a yard from the end zone, but it depends on a variety of factors. And so by that, supervisor learning by practicing is going to develop this really nuanced policy for selecting between those two strategies. That's the strategy pattern. But these evolved because I said, oh man, working on problem after problem after problem, you see these components. Last thing I'll say about it is each of these patterns is additive. So you can build a bigger agent design that has a strategy pattern, a perception pattern, and a plain execute pattern together based on the needs of accomplishing that task.
Yeah, 100. I mean, that's super interesting. And just before we dive into the platform here, I just want to kind of like get your thoughts on something, because I speak to a lot of end users and vendors on this platform, and I kind of like seen different approaches to multi-agent design. So in your case, really the agent is or a team of agents. They are about executing a specific task. I've seen also this idea that an agent is a digital twin, right? Where you've got an agent for a specific piece of equipment or an agent for a work order. What are your thoughts on how
I'm
this?
glad you asked this because I think the concept of digital twins blurs two fundamental things. Feedback and action are two separate things. So feedback tells you what will happen if you do something, and action is the something you should do. Those are fundamentally different things. And a digital twin, I understand why people do it, but a digital twin blurs both of those things together. And sometimes blurs the perception together also. And then also adds the data collection and the actuation. So I always try to separate feedback from action. Are we talking about is that this thing giving me feedback as to what will happen? That's what simulations are. Or is this thing telling me what to do? That's what controllers and agents and optimizations do. I assert that agents tell you what to do. They're not feedback mechanisms. They tell you what to do. And so that's the first thing. The second thing is you might have an agent for each machine if the machines need to work together. So think about a wind farm. In a wind farm, there's 20 to 50 or even 100 wind turbines. And how each turbine behaves affects the other turbines. They have a wake behind them. So if I'm the one in the front and I turn this way, the ones back here will produce less because of the turbulence that I just exposed them to. So they actually need to work together. In that case, I will use a set of agents that coordinate with each other. We call those in our platform coordinated skills that cooperate and work to get that learn together and basically communicate and say, well, this is what I'm about to do. Make sure you watch out for that and optimize across the whole system. So sometimes that is a very valid design pattern, but that is not the only design pattern.
100%. Okay, so let's bring all of that down to the AMESA platform itself. Could you maybe give us an overview of AMESA? How does the platform sort of like pull together everything we've been talking about? The machine teaching methodology, multi-agent orchestration, and kind of like this idea that you've got like a proving ground concept into this one unified system.
Absolutely. So there's really three parts of the AMESA platform, three products in the AMESA platform. One is what we call the Agent Orchestration Studio. So imagine a no-code platform where you can define agents, you can drag and drop agents into a team. So into this kind of like graph-looking, N8N kind of looking structure. Now, there's two ways that those agents can get there. You can actually use an API to publish existing algorithms, controllers, or even LLM agents as agents. So you can use a CLI. You could say, I want to publish this agent that I already created, and boom, it pops up in the Agent Orchestration Studio, and now I can drag and drop it. But you can also define agents from scratch. So it's kind of like your team builder. That's the Agent Orchestration Studio. The second is, and this is one of the really differentiating things about our platform, is our agents learn by practicing. They don't just talk to each other. So you need a place for them to practice. And so our training infrastructure where the agents practice on a simulation and get feedback, we call that the AMESA Agent Cloud. So you can train agents on your Kubernetes clusters that are hosted in your cloud environment, that are hosted in our cloud environment, even on local machines or single machines. And then the third part of the so after you train these agents in simulation, you'll benchmark them and you'll mark different ones as ready for deployment testing. And then the third product in the AMESA ecosystem is the runtime. So the runtime is actually what connects the agents, usually on the edge, to the actual factory. You can connect them directly to the PLC. You can connect them to an IoT platform. You can connect them through an API to software in your IT environment also. I'll mention one other piece. We don't have it as a formalized product right now. It's part of the Agent Orchestration Studio, but we have the ability to, from data, create specialized digital twins, create simulation models for your task based on your historical data.
Right. So maybe let's focus a bit more on the Agent Orchestration Studio. And again, this is an area where I've also seen friction or a tension really in industry, where some solutions they externalize the difficulty of kind of like really building these AI agents. And I want to get a sense, from what does that actually look like when an engineer sits down, to design a multi-agent system?
Yeah.
What sort of knowledge do they need to, or what sort of skills do they need to have,
Yes.
or what sort of like built ideas do they need to have?
So you don't need to be able to write code. So you don't need to write any code. What you do need to, you can, but you don't need to write any code. You do need understanding of the problem, which our assumption is that every engineer knows that about their process. So for example, first thing you set is, what is the overarching goal or the KPI for the multi-agent system? This multi-agent system is supposed to be maximizing yield. And then you provide an ROI statement. A 1% increase in yield is worth, $3 million a year. Okay, cool. I set that. The second thing you need to set is, what are the different scenarios? Okay, there's a high demand scenario, there's a low demand scenario, and those are initial conditions for practice. There's a startup scenario, there's a steady state scenario, there's a shutdown scenario. Those are things that the engineer knows also, and you can define these without writing any code. You just go into the interface and drag sliders and click them and set up all your scenarios. And then it's time to actually set up some agents. Now, each agent is going to have goals, constraints, and success criteria. This is also something that every engineer knows. So what do I mean by this? Well, in soccer, the goalkeeper has an exact opposite objective as the striker. The goalkeeper's objective is to minimize the amount of goals that are scored by the opposing team. He actually doesn't care at all how many. His job doesn't care at all how many goals his team scores. The striker is the exact opposite objective. So you see, for each agent, you go in and set what's the objective for that agent. Then the constraints. A goalie is only allowed to touch the ball if he's within this boundary box, the keeper's box on the field. Same thing for your agent. You can say, I want you to avoid these spaces. I want you to stop practicing and start over if you go out of these bounds. Those are constraints. And then success criteria is, how do I approach success? Like, how do I get an on-ramp to the good regions? And also, when have I succeeded? When should I stop because you succeeded? These are all things you can set in our platform, define in our platform for each agent without writing any code.
Okay. And when it comes to the agent cloud, which you've said is really what differentiates AMESA from other multi-agent platforms, can you kind of like give us a more detailed look into how that simulation driven training looks like in practice, and specifically, how do you sort of like make sure that this digital training environment is faithful enough that performance translates to the real
I
world?
understand. So as part of our simulation lab, we have two scores and a bunch of data plots. So the first score is the data score. Now, the data score tells you how good a feedback that data is going to be for for this problem. So let me give you another simple example. Let's imagine you're building autonomy for a self-driving car. You have a data set about the car. Now, and we're talking about just lane change maneuvers. Okay. So a lot of times we get these data sets with many, 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 many fields in them. And so acceleration for the vehicle, super valid feedback. Required. Velocity of the vehicle, yes. Lane position, yes. Oil temperature, no. That's not useful feedback for a lane change maneuver in autonomous driving. And so our platform will tell you this has a low data score, and it will tell you why. It's because these fields that you've included are not relevant feedback. And if you remove these fields, you'll actually increase the data score to 92%. So that's the first thing, is this data good feedback for this task? The second is this simulation representative of reality? Now, you don't want a simulation that's exactly represents any particular plant or machine, because then an agent or a human could just memorize what to do. You want something that's representative. So you're not actually training on the data. You're training on a model that's representative of the data that you can vary.
Mhm.
So we'll provide graphs for each and every core variable that show the distribution, or show the outline of what the data looks like, so that an expert can see, okay, good, that's representative. It's the right shape. I don't want it to be exactly the same, but it's the right shape and it's within tolerance. And then we'll provide a simulation score that gives you a single index that says, oh yeah, simulation score is 98. Great. This is going to be representative, and you're going to get some good agent results from training on this.
Okay, so I mean, once those agents have sort of like proven themselves in the agent cloud, how do they, make that jump into, production? Considering that, overwhelming majority of plants have got some legacy, systems, legacy, S, PLCs. What does that integration look like from training into real production environment?
Perfect. So we have two products. One is the AMESA Runtime Server, and the other is the AMESA Runtime App. So the AMESA Runtime Server is for folks that already have adopted IoT platforms. So I'll give you some examples of IoT platforms. Siemens Industrial Edge, uh, Microsoft IoT operations, Azure IoT operations, Rockwell Optics. These are all platforms that connect to the PLCs and provide essentially an API for some protocol. OPC UA, MQTT, HTTP. Our runtime server will inference the agent. This is all on the edge. So on a local, CPU based, Linux or Windows box. So standard piece of hardware that's sitting on the edge inside the OT network. It gets the agent's action. It sends it through MQTT or one of the other protocols to this IoT. The IoT talks to the PLC. The PLC says, this is what happened. It gets passed back. That's what the server does. Now, some folks say, well, I haven't adopted any IoT software. Or my IoT software doesn't, support the kind of things we're trying to do. That's what the app is for. The app is, it's a Linux application you can install right on your edge machine, and it will talk directly to the PLC tags.
Okay, so it does support like some common industrial communication protocols, like
Yes.
Yeah.
Common protocols and direct communication with the PLC where necessary.
Okay, perfect. So, I mean, one of the big challenges that I see a lot with manufacturers is that you build this AI agent or AI solution for one specific line, but as soon as you want to scale that into different lines or different sites across your entire enterprise, then this is kind of like where everything falls apart.
Right. So let's talk about that. I almost mentioned something about this earlier, but this is the right time to talk about it. This is the kind of reproducibility or the reusability of these agents. So this is where the operating regions are really, really important. So, for example, most of the time we go in and folks will say, we have 100 plants or 100 machines or 100 formulas or 100 recipes. That doesn't mean you need 100 agents. Why? Because a bunch of those machines, formulas, or recipes are alike in the way that you need to control them. So our algorithms will say, okay, out of those 100, you actually only have 6 groups. These recipes are like this, these recipes are like that, these recipes are like, and we'll actually show it to you on a visual graph. If you train an agent that learns how to control in that operating region, then any machine or recipe or formula that resides in that operating region will be controlled well by that agent. So when I'm deploying to a new recipe, I developed a new recipe or a new plant, new formula, you rerun those algorithms and you say only one or two things will happen. Either, oh, the new one is in one of these operating regions. Great, we already have an agent that has proven to work well in that operating region, or there's a new operating region that now there's a 7th operating region that this plant belongs to. In that case, you extend the training. You don't have to start all over. You extend the training by training one new agent for that operating region. And then from then on, any other formulas, plants, machines that belong in that operating region are covered by your existing agents as well.
Okay. So when it comes to deployment for AMESA, what is the typical approach for deployment? Is it deployed in the data center? Is it in the on-site, on-prem?
On the edge, in the OT network. So we've had a few folks that have said, "Oh, we have this IoT platform, and we prefer you to pass the agent to pass the decisions in the cloud, which will go down." And sometimes there's digital twins that do the same, but overwhelmingly, like almost all, there's the agents, the AMESA runtime app or AMESA runtime server with the agents are sitting in the OT network, not connected to the internet on the edge.
100%. Okay, so I think you've already kind of like given us a few example, real world example of your customers. Can you maybe just give us a picture of where or who is using this kind of solution or the AMESA platform, like with some real world examples?
Yes, we have. So we have 6 Fortune 500 customers, a bunch of other large manufacturers that are not in the Fortune 500, and then a branch of the U.S. military that is using our agents. Now, let me give you a couple kind of patterns. There's the two most common things that folks are doing with us is something related to chemical process control. So manufacturing chemicals, CPG, consumer product goods, including food, is in that category, and oil and gas is in that category. Why are there so many folks using it for that? Because chemistry is extremely nonlinear and hard to understand. And so it's one of those things where you can't kind of calculate your way out of it. So process manufacturing is our number one. That's the number one thing people are using us for. And the second is logistics. So that's another one where there's extreme variation, as the economy changes and demand changes and in season and out of season for different products, imagine like travel things, then the outlay shifts in a way that makes it difficult for optimization algorithms. So things like scheduling warehouses, scheduling rail yards, inventory optimization. So supply chain and logistics is the number 2 area that folks are asking us about and working with us on.
Okay, so for any manufacturing leaders who are listening to this conversation right now, and then they're saying, okay, this is what we need. How do they engage you? What's the process typically like? And also interesting for me to find out from you is how often do you go from initial engagement to the first sign of value, or we start to see some value from it?
I appreciate that question too. Our average project, our average initial project, whether it's done by one of our system integrators or whether it's done by the company themselves on our platform, is about 12 weeks. So you can go, we call it the data to autonomy flow. You can go from data to agents that you're ready to try out in the factory in about 12 weeks. And there's a variety of ways to engage with us. You can engage with us directly And we love talking to folks about their use cases, but we also have a great set of system integrators all around the world that do this work also. And we'll actually go to the plants and do subject matter expert interviews and things like that.
Absolutely. Yeah, so we're going to provide links to the AMESA website. We're going to provide links to Ken's LinkedIn account and all the relevant material that I made reference to on this session. But before I let you go, Ken's, we have a tradition here on this podcast where I kind of like put you on a spot and kind of want you to get a sense of your prediction. What's your prediction on what the plant flow of the future would look like? So, I mean, you can pick any period, the 3 years from now, 5 years from now, 10 years from now.
I think of it as a little bit like Tale of Two Cities. I think there's going to be a bifurcation where there's going to be a pursuit of quote unquote gigafactories, which are these, brand new from scratch, IoT, AI first, very, very automated with robotics factories. Those are extremely capital intensive, and you can't do that in all cases. And then there's going to be the other side, which is what we primarily work with, which is humans and agents together learning and teaching each other and optimizing these plant floor operations.
Awesome stuff. Kens, this has been such a fascinating conversation.
Great questions. They're really good.
Thank you so much. Thank you so much for taking the time. If you've got any last words for our audience, please do go ahead. Anything you want to mention, or is anything they should look out for in the roadmap, or anything really?
No, this has been great. It's a great conversation, and thanks for the topics that you brought up.